Young's modulus of a material is the ratio between tensile stress and tensile strain within the proportional limit of that material. In order to calculate the Young's modulus, you can use these equations. These are the same equation but written in three forms. So F over A is the tensile stress, E over L is the tensile strain, and this Y is the Young's modulus. These three are the same equation written in different forms. So in this experiment, we are going to find the Young's modulus of a metal, which is steel. So here we have these two steel wires attached to a rigid support here, and one of which wire is attached to a main scale and another one to a vernier scale. So the string attached to the vernier scale is going to be submitted to different loads, and according to those loads the wire is going to be extended. Then we are going to calculate those extensions against the load we applied here, and using the above mentioned equations here, we can find the Young's modulus. We are going to use a graphical method to find that. That's why we need several readings for loads and the extensions of this wire Q. Both of these wires are steel wires. So first, let's consider the materials and apparatus required for this experiment in detail. Obviously, you need these two steel wires. The reason for using two steel wires will be explained later. One of the wires is attached to a main scale and another to a vernier scale. And the wire attached to the main scale is submitted to a dead weight. So we are not going to change the mass of this part. The wire attached to a vernier scale is attached to a pan, and we can load some weights onto that and change the load applied to the wire Q. So for the experiment we need two steel wires, each about 3 meters in length and 0.5 millimeters in diameter, and a main scale like this and a vernier scale. Then this dead weight and a pan in order to load some weights. Then half kilogram weights. Those half kilogram weights will be added onto the pan here. Then we need a meter ruler and a micrometer screw gauge. The meter ruler will be used to measure the length of the wires, and the micrometer screw gauge to measure the diameter of these wires. So that is the materials and apparatus required for this experiment. Then let's consider step by step in detail in order to continue this experiment. First, you have to attach the dead weight into the wire P with the main scale. Then you have to attach the pan into the wire Q with the vernier scale. So there's no additional weight added here. Still there's no half kilogram weights added to the pan. Then you have to take the reading from using the main scale and the vernier scale. Let's say that the reading taken from the vernier scale is 12.15 millimeters. So this 0 means there's no weight added to the pan. So at that instant, the reading of the vernier scale is 12.15. Then I'm going to add a half of kilogram into this pan, and again take the measurement from this vernier scale. Let's say now the reading is 12.25. So it is obvious that the wire has extended due to loading of half kilogram into the pan. Now the weight on the pan is half kilogram, and the reading from the vernier scale is 12.25. Then I am going to add another half kilogram. Now the total load on this added on the pan is 1 kilogram. Now the reading can be like 12.35. And I have to keep doing this procedure in order to find the extensions of the wires. Then let's say for the 1.5 kilogram, the reading is 12.45, and for the 2 kilogram reading is 12.55. For this one it is 12.35, 65. For 3 kilogram 12.75. So those are the readings against the load applied on the pan from the vernier caliper. So you can clearly see that the readings have been increasing. It has been increasing. So it is a sign that the wire, this Q wire, is extending against the load applied here. So we have gained readings when we are loading onto the pan. So this column represents the readings taken when we are loading. In order to minimize errors, we have to take readings when we are unloading the pan. So let's say here we have added 3 kilograms already, and the reading, we have still removed any weights, so the reading here also should be 12.75. Let's say now you have removed half of kilogram here. Then let's say the reading is about 12.64. So you can see now the weights on this pan is 2.5 kilograms, but the reading has changed a little bit. This could be due to the extension of bends and kinks. I will explain that later. So the reading is here 12.64. Then we are going to remove another half kilogram. Then the reading could be like 12.54. So the reading is decreasing now since we are unloading this. Then for this one, let's say 12.46. Then we are going to remove another half kilogram. Then the reading could be 12.36. Then here for the half kilogram, the reading could be 12.26. And here the reading could be 12.16. So there's a distinction between readings when we are loading and when we are unloading. So using these readings, we can calculate the extension of wire for the applied load onto the pan. Then we need to take the length of the wire Q. So you have to use a meter ruler for that. Using the meter ruler, you can measure the length from this rigid support to the beginning of vernier caliper. So this length is considered as the length of the wire Q. Then you have to measure the diameter of wire Q. So for that, we are going to use the micrometer screw gauge. You will have to measure the diameter of 3 places of the wire. So usually what we do is, so if the wire is like this, you have to take the reading from at a one place, the reading from 2 normal sides like this, and take the average of that one, and you have to do that for 3 places of the same wire. then you can calculate the average of that, and that value is considered as the diameter of the wire. Then let's see how to calculate the extensions of the wire. So if we take this first reading, that is 12.15 when adding weights, but here we haven't added any weights into the pan, so this reading is considered as the original length of the wire. So this column represents the extension when adding weights. We haven't added any weights, so it is considered as the original length. So the extension should be 0. Since till there's no weight added onto the pan, this length is considered as the original length. If the wire still has the original length, the extension should be 0. So in this case, that is when you add half kilogram, the reading is 12.25. In order to find the extension in this case, you have to reduce 12.15 from 12.25. And the reading, the extension should be 0.10. So from each of these values, you have to reduce a value of 12.15. So for 1 kilogram, the extension should be 0.21. You have to reduce 12.15 from 12.35. So you have to repeat this process in order to find the extension. Then you will get, for this one, you will get 0.30. For this value, you will get 0.40. This one, 0.50. For this one, 0.60. So these are the extensions when adding weights into the pan. You have to do the same thing for this column as well. So this when removing weights, the initial length is considered as 12.16. So the extension, there is no extension here, so it should be 0. In order to find the extension when you have added half kilogram into the pan, you have to decrease 12.16 from each of these values. So here, if you remove this value, it could be 0.10. For this one, it is 0.20. For this one, it is 0.30. For this one, it could be like 0.438. For here, it could be like 0.48. For here, it could be 0.59. So these are the extensions for each load applied to the pan. So you have an extension value when adding weights and when removing weights. Then we are going to calculate the mean extensions values. So for that, you have to take each row when adding weights and when removing weights for extension. So you have to add these two and divide it by 2. And 0 plus 0, that is should be 0. If you add these 2 and divide it by 2, it is 0.10 still. Then again for this column as well, it is 0.20. For this column, it is 0.30. For this row, it could be a 0.78. So if you divide it, it should be 0.39. For this one, it should be like 0.49. For this column, it could be 0.59. So these are the mean extensions values. Then what we are going to do is to draw a graph against the weight applied on the pan and the mean extensions values for those weights. So in order to draw the graph, we only need these two columns, that is the weights on the pan and the mean extension values. We needed all those columns in order to find the mean extension of the wire. So for the y-axis, I'm going to use the extension values. So let's say the extension is E and it is measured in millimeters. And for the x-axis, I'm going to use the variable weights on pans. Let's say that is simple M, and it was measured in kilograms. So when the weights on the pan is 0, the extension is also 0. We made it by default. So the first starts from here. That is the origin of the graph. Then let's say this second reading, kilograms, that is half a kilogram. Then the reading is 0.1, the extension. So that coordinate should be somewhere here. So you have to mark all these coordinates on the graph. Let's say here, here, here. So we have like 6, 1, 2, 3, 4, 5, 6, 7. 7 readings. 1, 2, 3, 4, 5, 6, 7 readings. Then you can draw a line across these coordinates. And the graph will be something like this. Once you draw the graph, we can calculate the gradient of the graph. In order to calculate the gradient, you have to find a furthest point on the graph. Let's say it is somewhere here. Then you can calculate the gradient. The gradient of the graph, let's say this reading is here is x and y. So the gradient tan alpha is equal to y minus 0 divided by x minus 0. So from this one we can calculate the gradient. Then let's see how this gradient value related to the Young's modulus. So I'm going to choose one of the equations from here. Since E is the y-axis, I need to subject E from these equations. So if I choose this equation, I have to subject E, and the equation will be like F L over AY. This F term, that is the force or the load on the Q wire. So that load we taken as M, then you have to multiply that by G. Then it is converted to the load on the wire. So Y, that is the the E, that is the Y variable here, which is the dependent variable. Then for the X, it is simple M. So I'm going to leave G here and L here, then AY. Then I take simple M out here. Then this simple M is going to be the independent variable. So this part of the equation can be considered as the gradient, which is simple M. Already we have calculated the gradient value, that is simple M. I'm going to say M dash. So this M dash value, as you can see from the equation, M dash value is equal to G L over A Y. So we have calculated M dash value. So we know this one, that is the gradient of this graph. G can be taken as 10 meters per square meter. That is the gravitational acceleration. Then L, length of wire, we have measured it, and capital A, cross section of wire. Using the diameter reading of the wire, we can calculate the cross sectional area of the wire. Only unknown term is this capital Y, which is the Young's modulus of the steel. In this case, it is steel. So that is how you can find the Young's modulus of a metal. We have to follow this procedure in order to minimize errors when experimentally finding the Young's modulus. So there are some special notes to consider when finding the Young's modulus in order to minimize errors. We could have done this experiment using only one steel wire, but we have used two steel wires like this. There's a reason for that. As you know, there can be temperature ranges while we are doing this experiment. And due to the temperature changes, the wires could expand. But since we have used two steel wires, so those two wires are made of the same material, there can be variations of length, but since the length variation happens identical for both of the wires, that length variations due to temperature is minimized. That's why we need two steel wires. We could have done that using a one wire. We could have measured the extension of that single wire, but we have chosen two steel wires in order to find the Young's modulus. So that is one concern you have to think about. Other one, we are using a one rigid support in order to hang both of the metal wires. As you know, when you attach one wire from a rigid support, there can be a yielding like this on the support. So if I have attached other steel wire on a different support, the yielding could be different. But since we have attached both wires into the same support, we can say that the errors due to this yielding is minimized. So for both wires, the yielding from the support is the same. So that error also is minimized. The another thing you have to think about is a wire can have bends and kinks originally. So when you are applying loads, those kinks or bends could extend and cause an error. That's why we have to take extension values when loading and unloading. So you have taken the readings when loading and unloading. In that way, you can identify whether the wire had bends or kinks. If you remember the previous table, you can clearly see for the same load, the reading value from the vernier scale is different in some cases. The reason for that is the wire having bends or kinks. So we have taken in two instances, when loading and when unloading, the extension values. So we have taken the average of those values when loading and unloading. So that taking average value can minimize the errors due to bends and kinks. So those are some of the notes in order to minimize the errors when we are finding the Young's modulus of a metal. If you have any more suggestions in order to minimize these errors, let me know in the comment section.